In this video, we're going to learn how to check for continuity using three rules. So we can say that a function f is continuous at x is equal to a if um, f of a is defined. The second condition states that the limit as x approaches a of the function f of x exists. Okay, and finally, the third condition, the limit as x approaches a of fx is going to be f of a. Okay, let's see. So let's draw a few graphs to see graphically how we can determine continuities and discontinuities. Okay, so suppose I give you a simple graph like this, where I have a straight line and I have a hole here. Okay, so a hole means that at x is equal to a, this is going to be the x value of interest. X is equal to a. The f of a is not going to be defined. Okay, so now we violated the first condition, right? Because if there's a hole, it means that f of a is not defined, right? So condition one fails. So we can say violated. Okay, now let's check for the second condition. The limit as x approaches a of fx exists. Well, in order for the limit to exist at this x value, both limits on both sides of this x value must agree. So from the right to left, the function approaches this value, the f of a, and from the left side of this x value, we're also approaching the same value, right? So the limit does exist because the limits on both sides agree. Now let's check for the third condition. So the limit as x approaches a here of the function indeed is f of a, right? That's the limit, right? Because we agreed that that's the limit, f of a. However, f of a is not defined, right? Because there's a hole. However, the third condition does work out and is satisfied. But since the first condition is violated, then this function is not continuous at x is equal to a. Okay, let's do one more, a couple more examples. So if I give you something like this, okay, and I'm gonna draw an asymptote this time here, and this asymptote will be the line x is equal to a. So I'm gonna draw a function like this, broken up into two pieces. So let's see, and when I say asymptote, it means that the function will never hit this x value. That's what asymptote is, okay? So as you can see, f of a is already undefined, right? Because asymptote means that the function will never use the x value of a because it's an asymptote, right? So f of a is undefined, okay? Because as you see, the function goes infinitely to the right of this line, x is equal to a, right? It's infinite. And we cannot measure infinity because it's undefined, right? It's not a quantity. And on the left side, it goes to negative infinity, right? So it's undefined, the function value of a. So condition one violated. Okay, well, let me measure these x and y's. So violated the first condition. Now let's check whether the limit exists. Well, the limit as x approaches this value from the right, the a value, goes infinitely up, and to the left of this x value, the function goes infinitely down. So the limits do not agree, right? Therefore, the limit does not exist. So condition 2 also fails. Okay. Now the third condition will fail for two reasons, right? Because f of a is not defined, so we can never really get there. And the limit doesn't exist as x approaches a, right? So there's no way that we can satisfy the third condition as well. So it fails. So this function is definitely not continuous at x is equal to a. Let's provide one more example. So here I'm going to do something like this. So suppose that there's a hole here and we have a curve increasing to the right, and this will be a shaded point here, and both of these points, I mean the hole and the shaded point, are on the same line, x is equal to a, and it's a straight line here. Okay, so you might say, well, let's see which condition this violates. Okay, so f of a is defined. Is f of a defined? Yes, right? Because this is shaded, so f of a does exist. Now let's see, limit as x approaches a of the function value. Well, the limit from the right to left of this line x is equal to a is this hole here, but the limit from the left to right as x approaches a from the left, the limit of this function is going to be the x-axis, right? This point here on the x-axis where y is equal to 0. So no, the two limits do not agree on both sides, so the limit does not exist. Okay, so condition 2 fails. Now let's see condition 3. As x approaches a, the function value will approach f of a, the limit, right? But as we just noted, the limits do not agree because one of the limits from the right to left goes up to the hole there and not the function value at the x-axis. So generally when condition 2 fails, condition 3 will fail as well. Okay? So for two reasons, obviously, this function is not continuous. Let's provide one more example. Let's see what we're going to do. Which example that's going to be. So, okay, I know what I'm going to do. So, this is the x and this is the y. So suppose I give you a straight line and there's a hole here, right? But I will draw a point here. And this will be the line of interest, x is equal to a. So now let's see which which conditions for continuity this example fails. It violates. So the first condition says f of a must be defined. Well, it is defined, right? This is f of a. So condition 1 holds. The second one says the limit as x approaches a for the function must exist. Well, on both sides of this line x is equal to a, we seem to approach the same value at the hole here, right? So the limit does exist. So we're not violating condition 2 either. Now let's check out the third condition. It says that the limit as x approaches a of the function must be the functional value of a. But is that true? I mean, the limit that we just discussed was the hole on both sides, right? So the limit is the hole, not this f of a, not this point here. So no, the third condition in this case is the only condition that is actually violated. So for this reason, this is still not a continuous function. So hopefully you understand more or less what continuity is. Please subscribe, and I'll see you in my next video. We're going to talk about more continuities and removable continuities as well.